Today, we're going to talk about just low degree testing. Okay, so I will not sort of recall what is the verifier that we discussed last time. We just want to sort of talk about the problem of low degree testing. Okay, so let's do that. Also, unlike for many other topics in this course for which there are not very many references in the literature that are helpful, this particular topic actually has good references if you're interested. I will link both from the website. Maybe they're already linked from it. One of them is Madhusudan's PhD thesis. It's a great reference for some of the early and elementary low degree tests. Another one, there's a book on property testing by Oded Goldreich, published, I think, maybe last year or the year before. And one of the, I won't say chapters or sections is on low degree testing, and it's a sort of very polished presentation and rather pleasant to read. So this is actually something that you can read up and learn more about it with good material. Okay, so if you remember, our goal was that you give me an m-variate function defined over f to the m. Okay, so it's a function that maps an m tuple of field elements to a single element. And we want to check that this is a low degree multivariate polynomial with a small number of queries. However, what we have seen already was a sort of much simpler task, was linearity testing. So before we get to multivariate testing, we'll look at a slightly simpler problem, okay, which is low degree testing for univariate functions. Okay? So we're going to look first as a warm-up at univariate polynomials. They don't suffice for what we discussed last time, but it's a very good warm-up. So in this case, we're given an oracle. It's a function from f to f. Okay? We can think about it as an explicit input as a tester is, well, okay, you should give me a description of the field. What else you should give me? Well, the degree. So the degree bound. Notice that in linearity testing, there is no degree bound. You just know what the degree is, right? So here we have some degree. And our goal is we want to decide if, or rather, we have these two conditions that if f has degree at most d, then we want to accept with probability 1, okay? And if f is far from all degree d functions, then want to reject with probability at least a half. Okay, so this is our goal. By the way, what does it mean for a function to have a certain degree? It means that you can find a polynomial, univariate polynomial that agrees with that function and it has that degree. Okay, so throughout today, I might say function or polynomial. When I say polynomial, I mean like the evaluation of that polynomial, right? So, okay. So, okay, so here we are. I'm a tester. Here's the function. I need to query it and decide, what to do. What should I do? What's a natural test? I should say T for test. So what did we do in linearity testing? What was kind of the first step in linearity testing? or if you don't want to think about linear testing, what do you think might be like a reasonable test here to do? It's a great idea. It's exactly what we're going to do right now. So a polynomial of degree d is uniquely determined by d plus 1 values. Okay? I could query d plus 1 values. Notice that whatever answers I get, even if they're like trash, they will define a degree d polynomial. Okay, so I probably will have to make at least one other query, because if I just make d plus 1 queries, then no matter what I read, whatever I read is consistent with a degree d polynomial, right? Okay, but then I'll just make one other query, okay? And check that whatever polynomial is defined by the first d plus 1 is consistent with this other query. Okay? So let's look at this test first, okay? So a very natural thing to consider. Let's call it a simple tester. And actually, for a moment, I want to sample all of these points at random. There's no particular reason, but it's just easier to think about. So I sample x0, x1, blah, 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 up to x d plus 1. So it's d plus 2 points in total. Okay. I query f at all these points. And I check that if I interpolate all these, I get a polynomial of degree at most d. Okay? Notice that this check is equivalent as saying I interpolate the first d plus 1 points, and I check that whatever I get, when I evaluate it at the last point, I get the value that the function says. Okay? So that's the test we're going to look at. Why is this a slightly non-trivial test? Because, I mean, first it depends how large is d, right? So you can think of d as 7, right? And that's maybe not so bad because maybe the size of the field is very large. Okay? So this is better than reading the entire function. So we're going to prove, it's a simple lemma, that the probability that I accept a function f if it is at least 1 minus epsilon, then the distance between f and polynomials of degree at most d in one variable is at most epsilon. Okay? Somehow, if I reject with not too high probability, it is because I'm not too far. Okay? Okay, so let's define a quantity epsilon 0 to be precisely the distance of f to low-degree polynomials. Okay, it's defined, right? I mean, I pick f, whatever it is, it will have a closest low-degree polynomial. Now, for any choice of x 0 through xd, so the first d plus 1 points, there is some polynomial h that agrees with the values f of x0, just by interpolation. That's whatever we were saying earlier. I'm saying let h be that polynomial. Okay, so you can think of h as a random variable, right? So you have sampled x0 through xd, okay? And they determine and then together with the values of f at these points, they determine the random variable h. Okay? Now, with this definition, then it's pretty easy to kind of conclude the proof. The probability that I accept f, it's exactly the probability that there exists f tilde in, or maybe let's call it f hat, in f hat as a univariate Ludwig polynomial, such that f hat of xi equals f of xi for all I going from 0 to d plus 1. Okay, so this is the, I mean, that's the condition under which I accept by definition. Okay? Now, this is at most the, or we can also write it as, yeah, let's just say at most, the maximum over x0 through xd, and I take the probability just over d plus 1, such that h, which that is determined by x0 through xd, of evaluated at that point equals f. Okay? But this is at most h, notice, is one of the things that I consider when I compute this distance. Right? Maybe it's not the closest. I don't know, right? But you know, if it's not the closest, it can only be farther, right? So this is at most 1 minus epsilon 0. Right? And this entire thing is at most 1 minus epsilon 0. And in fact, kind of even before the analysis, we noticed that to some extent it doesn't really matter. It doesn't matter that I'm picking x0 through xd at random. I could have fixed them to be the first few points, right? So, this is the end of the proof, and so we note that kind of can fix x0 through xd to be, I don't know, first d plus 1 points in f under some canonical ordering. And really the only kind of testing that is happening to me is through the randomness of xd plus 1. Okay? And maybe one way to feel it is, suppose that I wanted to make the relation, suppose I wanted to amplify the soundness error of this test. What is one way I could do it is I rerun the entire test. Okay? But what's a good way to do it that is maybe more efficient? Maybe this will give you like some intuition of how the test is going. Sorry? Yeah, I resampled the last one, right? So I don't really need to resample all the others because I didn't care about it, right? So you can think about that for every extra query that I sample, okay, I get another epsilon, right? So kind of with order of d queries, which you can think about as 2D, I already have my sort of a soundness error of being like, you know, super small. Okay? Anyways, so that's a test, and it works. So, note a couple of things. Like in linearity testing, it is non-adaptive. So we'll see that, you know, most natural things that we think about are indeed non-adaptive. Okay, by non-adaptive I mean that, you know, you can all ask all your queries together. You don't wait to hear back answers from the function to decide what to ask next. And the query complexity is d plus 2, which is order of d, and is optimal. Okay? By the way, how would you formalize the fact that it is optimal? I mean, intuitively, you don't get any signal, right? If you ask D+1 query, if you ask D+1 queries, but formally, how would you actually prove that doesn't work? So I bring a test. It's asking D+1 queries, and I claim that it works. And you want to say, no, it doesn't work, right? What do you say? Yep.
You come up with one low degree function and one far from low degree function for which the test would see exactly the same thing.
Good, excellent. So this is going in that direction, but to make it a little bit more precise, you actually need to consider distributions. Okay, because these two functions would actually potentially give you different answers on different query sets, right? Because if the tester were deterministic, then you could just prepare these functions to have literally the same values. But the tester is probabilistic, so you don't know what he's going to ask. So you cannot just prepare the functions to be that. So what you do is you say, okay, let's consider distribution a random, say, degree D function, okay? And a random, say, degree 2D function, which is like very far, right? Like you should totally reject that. Both of these distributions restricted to D+1 points, will look the same, okay? And then, then this reaches the contradiction, okay? So this indistinguishability argument is, a rather straightforward way to kind of prove lower bounds on the query complexity of testers. Just for the record, there are other ways where one does it that are sort of very beautiful, and you can read about them in the property testing book that uses communication complexity arguments. So that's actually sort of the way you prove from sort of more serious lower bounds. In this case, sort of a rather simple argument suffices. But okay, fine. The problem is that, as successful as this test is, it is really unclear how to capitalize on it if we want to go to the multivariate case. In the multivariate case, if we just take the ideas that we uncovered here and we try to sort of directly extend them, what will happen? What will happen? Yeah.
I guess if you do it naively, the number of queries you have to make goes up.
Yeah, because if it didn't, we'd be happy. And I want to say specifically, like how many queries do I need to ask? So say that I have an m-variate function of degree D. Yeah, on the order to the m. Why? Because what are we currently doing? We're trying to say, okay, look, there's an object out there. Let me ask enough queries until I can fix it, basically, right? So I'm using the fact that a set of D+1 points is a so-called interpolating set for the function. So once I know enough information, I have fixed the object, I know what the object should be, and I just ask some other query to check that whether the object that now I have in my head corresponds to the one that is claimed to be out there, right? So if I have a multivariate polynomial, I'm going to need to ask on the order of D to the m queries. The exact number depends on whether D meant individual degree or total degree. Okay, so for example, in the case of individual degree, I would need to ask D+1 to the m queries, because this sort of hypercube of size D+1 is an interpolating set for polynomials of individual degree D. Okay? Now this leads to a very large query complexity, and in the setting of the proof that we saw last time, D to the m was on the order of what? Yeah, or n, really. Like we set, we had h to the m was like exactly n, right? And h is exactly D+1. right? Because when you interpolate something, you get degree sort of 1 less than the size of the thing, right? So it was order of n. So we would need to ask n queries, but that's precisely what we didn't want to do. So what we're going to do now is look at a different, possibly like, more baroque univariate test that has like worse parameters, but the ideas involved in that test naturally lead to a multivariate generalization. Okay? Okay.
I think I'm just not thinking about it quite right, but what prevents you from just like fixing all the variables except for one, and then just testing that one is low degree, and then just doing that individually for each one, and then I can with that.
I mean, that's a good thing to think about. Yeah. So the thing is, you get basically degreeness in only certain directions, but you fix to which variables the other points, right? So you can let's think of a bivariate function, okay? So what you really need to know is that you have here univariate low degree, here univariate low degree, here univariate low degree. So, okay, sure, you can fix it to this one, but like, what about the others, right? Okay. So you can't fix it to all of them and check to all of them. That will be too many queries, okay? So then you can say, well, I'll fix to a random one and I'll check it, okay? And this starts getting close to something that are called axis parallel tests. And today we'll be looking at non-axis parallel tests, but such things in general work, okay? And you have to argue that if on average things in this direction are low degree, and on average things in this direction are low degree, then it means that on average the entire thing is low degree, okay? This is the so-called row-column bivariate test. And we'll not analyze it here. It's actually not so easy to analyze.
What do you mean by on average?
Sorry? No, but you do the fixing at random, right? So if you pick the row at random and you check that a random row is low degree, then it means that on average it's low degree, right? All right, so let's do another attempt. So we're going to focus on the case where f is fp, okay? And we're going to assume that p is at least d plus 2, okay? Notice that the degree in our proof was itself polylogarithmic, so picking the field to be like this one, it's okay, okay? We're still in the univariate case, but when we move to multivariate case, it's going to be fine. So let's see a different local characterization, or let's see a local characterization of polynomials that look like that. So remember that we've seen local characterizations before, right? We said a function is linear if and only if for every x and y, f of x plus f of y equals f of x plus y, right? So here we're going to write some other local characterization for univariate polynomials. And it's like this. It says that for every d less than p, and for every function of that type, then there's a theorem that says that f is low degree if and only if for every, I see that I have x is overloaded for me. Okay, so I'll put inside here a big X, and because I want to use small x here. For every x, it holds that you have this linear constraint, sum over a certain d plus 2 values with certain coefficients. So I'll kind of put down these coefficients in a moment. So you take x plus 1, x plus 2, up to x plus d plus 1, okay? And you check whether certain things is non-zero, is zero. And this alpha I, they look a bit funny. it's minus 1 to the I plus 1 times d plus 1 times I. Okay, they're kind of like a bit of strange coefficients. The proof is actually not very enlightening. It's kind of boring, okay? Let me just say that it's in induction and derivatives. Intuitively, what's happening is that if a function has a certain degree and you derive it and you apply the derivative operator to it a certain number of times, at some point you get 0, right? If it had been higher degree, then you wouldn't, okay? So, and when you start deriving things, then you pick up coefficients of this form. So this is actually an inductive proof that says, assume that things look like this for all polynomials up to degree d minus 1. You want to prove it for degree d. You take your degree d function, you apply a derivative. What you get is polynomials of degree d minus 1. You apply the characterization, and you kind of come back up, and you get a characterization of this sort. Okay? So the one thing that should be intuitive is that we're putting a linear constraint on d plus 2 points. Okay? Remember that up to d plus 1 points, we cannot have linear constraints because those are independent degrees of freedom, right? The d plus, I mean, that additional thing is the first time you hit like linear constraint. Okay? Okay, so we might wonder, okay, fine, that's a local characterization. Anytime you see a local characterization, you have like basically a test. Pick a random x and check whether this is the case, right? That would be the, okay, but it doesn't work. Here's a counterexample. So take your f, okay, and put some polynomial p in the first half and some polynomial q in the second half, a different one. Can anybody explain why this is a counterexample to the test that picks x at random and checks that constraint? Yep.
You could be just checking one of the two halves, so you guarantee that half is low degree, but there's this other half, and that contributes to the total degree, but you know nothing about it.
Right, so with very small probability, I reject, because that happens only when my interval here kind of crosses the boundary, right? But that's not good, because this is very far from being low degree, right? It's 50% away, and yet I'm rejecting with probability that is maybe like, like d over f, okay? It's very small, okay? So it's no good. It's like this just is not a good test, okay? Because kind of your interval is, kind of depending upon the x is here, right? And it just doesn't see this sort of a combination of two polynomials, right? It's not a good test. So another lesson is that not all local characterizations lead to good tests, okay? Only so-called robust ones. But to some extent, the main problem here is that we have this interval that is really kind of compact, right? So what we can do is to kind of tweak the local characterization and make the step also random, the step size, okay? So maybe instead of stepping by 1, I step by a random amount. Intuitively, I should defeat this example, okay? If I step for a random amount, I come here, then I go here, oops, I'm already in some other place, right? Turns out that works, okay? So a corollary of the theorem is that, again, for every d less than p, for every function that looks like this, f is low degree, if and only if for every x and h in fp. Now you have this condition with the same coefficients, except that now we're taking steps whose size is also random. Okay? So deriving this one, so going from here to here is actually elementary. Okay? But I don't want to do it now. Maybe if we have time at the end of the lecture, I'll do it. Okay? But it sounds believable. Okay? Or maybe like, let me just say proof. Consider g of z that equals f of a x plus zh. Okay? So, and then you apply sort of this theorem to this function, and then you get back that one. Okay? All right, so now we have a new candidate test. You sample x and h at random. And you query f of x plus ih for I going from 0 to d plus 1. And then you check this sort of magical condition. Okay, so that's our new candidate test. Like the older test, it is making d plus 2 queries. Okay, it's just making them in this very sort of curious way. Now the theorem that we're going to prove now is that for every epsilon that it is at most order of 1 over d squared, if the probability that we accept f is at least 1 minus epsilon, then the distance from f to low degree is at most 2 epsilon. Okay? So let's just compare this statement with the previous one. So first we have a loss of 2 here. Oh wait, who cares? It's a constant, okay? But it's there, okay? But the more important thing, if anything, is saying that we are in the so-called high acceptance regime, okay? Only if our test passes with sufficiently high probability, then we're able to say anything, okay? So this is basically saying that really the query complexity of this test is not quite d. It's more like d cubed, okay? Because I have to make up for it, okay? To experience this one with constant probability, I need to run it enough times. I need to run it d squared times, okay? And say, okay, we had a perfectly fine test. It had actually query complexity d, was even optimal. Now it's like d cubed. You're running d squared times a test of order of d queries, and you get a 2 here. Well, the point is that, as we will see now, this test directly syntactically extends to the multivariate case. How? I just put a vector on top of everything. So if I so we need to analyze it, but I'm telling you what the test for the multivariate case will be. I pick a vector x and a vector h. And I check that starting from the point x in the direction of h, and I take steps in the direction of h, I will get a line, right? This is a line sitting in m dimensions, okay? And I check the same condition, okay? And literally the same thing holds, okay? So we're going to forget the multivariate case because it doesn't matter. Syntactically, you can just consider x and h as vectors, okay? So what now happens, though, is that the query complexity of d cubed is independent of m, okay? So that's why we win overall, okay? Now, we're going to come back to that maybe later. For now, let's go back to the m equals 1 case. So all of these red things are not there. Also, I should say in the multivariate case, we're testing total degree or individual degree? I did agree. It's total degree, right? How can we be testing in individual degree if our lines are all over the place? Right? This is a line in any direction. Right? So individual degree only pertains to axis parallel lines, right? So kind of coming back to the earlier discussion, in the Bivariate case, right? I can have individual degree this way, individual degree this way, but the moment I tilt my line, I see 2D, right? Or I might see 2D, right? So here, what we're doing is basically a random lines test. We're picking a random line in a random direction, and along this line, we're looking at steps of h apart, d plus 2 points. And we're asking, do I see a polynomial of degree d there, right? If the invariant polynomial, the invariant function is actually a polynomial of total degree d, then whatever line I look at, I should be seeing always degree d. Okay? And this is saying that if on average a random line looks like it has degree d, it is because the entire thing is close to half degree d. Okay? So here we're looking at total degree d. Okay? All right, but now we need to analyze the test, and we'll do it thinking of the univariate case. But before we start the analysis, are there questions about what this means? Yeah.
Do you need to have the points spread out even amount after, or could they have been like, could they have not have been random after you restrict to a line?
It's a good question. So depending on how you structure a test, the analysis will be different. So for this particular analysis to work, actually we do need you will see in the analysis, we actually use the fact that they are spaced out. Okay. Now there are other tests also that don't have this feature. So for example, you could choose to read the entire line. Okay. So that's f points. Okay. And that test also works. Huh? You could, for example, run that one, okay? But it works with better parameters, okay? So, or you can read, for example, 10 d points instead of d plus 2, okay? And then you can prove better parameters also, okay? So you do get, if you read more points, clearly you can sort of run as a routine the same thing as before. But if you do read more points, you can actually do more with analysis. And analysis will actually look different, okay? This is, as far as I know, one of the simplest analyses. Analysis of low-degree tests actually get pretty complicated. The nice thing about this analysis is that it is a direct extension of the combinatorial analysis for the linearity test that we've seen 2 weeks ago. Okay, it's basically that same strategy applied in this case. Okay, so that's why it's appealing, because to some extent you've seen it already. We'll be doing instead of majority decoding, we'll be doing plurality decoding. Okay, so more questions about that? Yeah.
I actually thought it was that we were looking at the individual degree, because I thought when we're looking at the two vectors that when we try and find the amount of the polynomial that connects the two, we want to check that the individual degree of that is like similar to the individual degree of the two lines. Can you go over again why it's total degree in this case?
Yeah. So let's maybe focus on the Bivariate case. Okay. So we have like a square, right? Individual degree means that every row and column, if I look at them, they are univariate polynomials of degree d. Okay? But this test is not doing that. This test is saying pick a random line in any direction. So for example, say the diagonal, and look at what is the degree on that line as a univariate polynomial. If I had individual degree d, what I expect to see on the diagonal is not d, is 2d. Because I am experiencing the degree from both variables. Okay? So if I have a bound on the degree across the sum of all variables, then that tells me what I expect to see on any line. Good question. Yeah. Okay, so now we're about to jump into an analysis. Okay, we're going into the trenches, and it won't come back out until the end of the lecture. Okay, so yeah. Okay. Okay, So in linearity testing, the first step of the proof was to define a function that kind of is our guess for what is a nearby good function that probably is low degree. Okay? And we use the notion of votes that somehow for every x, for any fixed x, over all y's, different y's had different votes on what the function should be. Right? Here we're going to do something similar. Okay? We're going to define a function g. I'm going to stop using fp and just write f. And it's going to say, take the majority or the plurality over h in f of the values that you get by summing from I equals 1 to d plus 1 alpha I f of x plus ih. Why this? Because remember, the first term in this expression is when I equals 0. It's f of x, right? And also, I guess I'm using the fact that alpha 0 is 1. I'm also using that thing. Or minus 1. Minus 1. Thank you. That's important because I'm moving it to the other side of the equal sign. So this is kind of the vote that h has about the value f of x, right? So let's call that, g of x is always, the most popular value, okay? Now, I'm calling it majority, but it's not really majority, it's plurality, right? Because now we're not in the Boolean world anymore. This thing can take upwards of f values. I'm just take the most popular one, okay? Take that value and give it to g of x, okay? All right, so that's our function. And the first thing that we did for linearity testing, and we'll do also here, is to say that g and f are not too far. Okay? Okay? That somehow by considering it this way, it cannot stray too far away from f. Okay? All right, so one way to prove it is as follows. So define S to be the set of x's where set of x in f where the probability that this expression agrees with f of x is not very high. So f of x equals sum from I equals 1, d plus 1, alpha I f of x plus ih is less than a half. Okay? Yeah, so this is saying these are the x's for which this expression, okay, over a random h sort of agrees with f of x on a small number of h's. Okay, now epsilon, the rejection probability of the test, is precisely the probability over x and h that f of x is not equal of sum from I equals 1 to d plus 1, alpha I f of x plus ih. Okay? Again, I'm using the fact that alpha 0 is minus 1. So this is exactly our rejection probability. Right? Okay. So this is at least the probability that x is in S times the probability that this event happens given that x is in S. Plus 0. Okay? So I'm just introducing this event and I'm saying, okay, look, whatever this was happening, either it happens when x is in S or when x is not in S. Okay? Now, this is at most S over P by definition. The probability that random x is in S is exactly the size of S over P. Okay? I'm discarding what happens in the other case, but let's look at this condition. What is this probability? is at least 1/2 by definition, right? I'm saying if you're in S, it means that you agree with probability at less than 1/2, so it means that you disagree with probability at least 1/2. And that's exactly what we're looking at here. Okay, so this tells us that S over P is at most 2 epsilon. And I want to claim that this tells us that the distance between F and G is at most 2 epsilon. Why is that? Right, so this is just, this is the case, so I think that's clear, right? So why can I conclude that if S over P is at most 2 epsilon, then the distance between F and G is not too high? Okay, so one way to see it is to say that when X is not in S, then f of x equals g of x. Right? Okay. So it means that this function is not too far. So this was also the first step that we did in linearity testing, okay? Then we had something that was kind of called a collision argument, okay? So let's try to sort of see the analog of that. And for that, I'm going to get rid of this part. By the way, also I wanted to bring your attention that here, if I had been working with multivariate polynomials, nothing would have changed. I just put vectors everywhere. There's like really nothing that all I'm using throughout is just the structure of the linear constraints that my test is running. That's all I'm really using. Okay? Okay, so next lemma, we're going to prove that for every x, we have that the probability over h that g of x equals sum from I equals 1 to d plus 1 alpha I f of x plus ih is, I have to move this line, at least 1 minus 2 d plus 1 epsilon. We had something similar in linearity testing, so let's prove it. So for every I can write the following expression. The probability over h1 and h2 that f of x plus ih1, yeah, sum over I equals 1 d plus 1. No, this is alpha, so j, because I is already outside here. F of x plus ih1 plus jh2 is that it's equal to 1 minus epsilon, or at least 1 minus epsilon. Why is that? I'm just renaming things. I'm just saying, look at, kind of less convinced. Yeah. This is kind of my x, right? Kind of my x. Kind of, we can think about it as x prime, right? And the fact that I'm taking a probability over part of it doesn't matter. Just fix it. What really matters here is that h2 is random. See, this is exactly what the test is doing. Okay? And the test is, we know it's accepting with probability 1 minus epsilon, so clearly this will be the case. And why am I writing like this? Because, I'm going to write something similar, and then we're going to do union bounds, and I want to prepare the proper notation. But all I'm saying is that, the test accepts the probability 1 minus epsilon, and I'm saying it, using funny, just renaming things. For every j going from 1 to d plus 1, I can write something similar, but where now the roles of h1 and h2 are reversed. So f of x plus j h2, sum from I equals 1, d plus 1, alpha I, f over x plus j h2 plus I x1. Again, I'm writing again the same thing, just differently. Okay? And I'm just making these statements independently. I'm writing 2d plus 1 times the same thing. Okay? But now, by union bound, what happens is that the probability over h1 and h2 that, so now it's the collision argument, that I equals 1, that if I sum from I equals 1 to d plus 1 of alpha I, f of x plus I h1 equals, so what I want is that it equals sum from j equals 1, d plus 1 alpha j f of x plus j h2. Okay, so I want this to be the case, and I want to claim that this is 1 minus 2 times d plus 1 epsilon. Okay? So this is I want to look at the probability that these two things collide over h1 and h2. Okay? In the identity testing, again, if you go back, we had similar thing. How do I argue this? Well, one way to argue it is I open up each of these. Okay? So this one, I can write it as a sum from j equals 1 to d plus 1, alpha j, okay, f of, okay, now it's my x here, x plus IH1 plus JH2, right? I can just open up these things, but how can I pay for that? I have to pay for that with this, right? I have d plus 1 such things with probability at least 1 minus epsilon individually, each one of them equal this expression. I can pay d plus 1 times epsilon to just write this, right? On this side, I can also do that. I can open up this one from I equals 1, d plus 1, alpha I, f, now my x here is this one, x plus jh2 plus IH1. Okay, I can also pay d plus 1 union bounds here, okay, from the same second expression. So here I'm using this thing, here I'm using that thing. But notice that these two things now are the same. Okay? Again, just a collision argument. Okay?
Then we pay 2d plus 1 epsilon total.
Because that's what's here. Yep. Yes. Fine. Now for almost there. For every a in F, we can define Q sub A to be the probability that the sum from that if you sum from 1 to d plus 1 alpha I f of x plus IH equals A. This is a probability over x and h. No, sorry, just over h alone. This is the probability that this expression is A. Okay? Then, if you remember, we looked at the square, right? We had what was it? Px squared plus 1 minus px, everything squared. This is the same expression. So what are we doing here? We're summing a bunch of numbers between 0 and 1. Whatever this sum is, it cannot be more than the maximum of any of them. Right? Because when you square something between 0 and 1, it only goes down, right? Oh, but I'm here. I think I'm using Cauchy-Schwarz. Yeah, I'm using Cauchy-Schwarz. I'm using the fact that it's sum to 1. And I don't want to open up Cauchy-Schwarz. But the point is, like, this is at least, is at most the probability that over H that this holds. Right? But because the point is that G was taking the most popular value. And here, basically, we're looking at the probabilities, who's popular, right? The largest probability will be the one that G of X equals to. Somehow I didn't put in my notes I'm using Cauchy-Schwarz. Okay. Okay, so now we've learned this about G. Okay? If you remember, the third step in linearity testing was to say that under a certain condition, G itself is low degree. Okay, and here we're going to say that if epsilon is sufficiently small, then we can argue that G is of low degree. Okay, and because we know that G is not far from F, then F is not far from low degree, right? That's exactly what we did last time for linearity testing. And notice that as epsilon becomes smaller, then the probability that G equals this thing becomes higher and higher. And our strategy to prove that the function G was linear was to basically make sure that sort of we have events that overlap that gives us like a witness that it's linear, right? And we're going to do the same here. Okay? Okay, last lemma. Oh, also we should say that here, again, I'm using the fact that it's univariate. I'm nowhere using it. I'm always using just the structure of the linear constraint. Okay? I could be putting vectors above X everywhere. There's nothing here that I'm using properties of univariate polynomials. Okay? Last step, if for every epsilon that is at most, I think here we need 2 times d plus 2 squared. Okay, this is the 1 over d squared that appears in the theorem there. Then G is low degree. Okay. Now notice that the reason why we're paying so much for making epsilon small enough is because we have a lot of union bounds here, and it's because the size of our constraint is pretty big. It's order of d. In linearity testing, it had constant size, right? So we didn't really feel this union bounds. What we felt was just basically saying that if the test rejects with probability less than 2 over 9 or whatever it was, then G is linear, right? So here we're sort of parameterizing everything in terms of d because it is a parameter we care about. How do we show that G is low degree? Well, we have a local characterization. Here it is, right? So I want to fix arbitrary x and h, and I want to show that that thing holds. I want to show that sum from I equals 0 to d plus 1, alpha I, g x plus ih equals 0. If I show it for arbitrary x and h, I know that G is low degree. Right? Okay, and if you remember last time, the way we did it is we invoked this statement with different choices of x, and we rewrote it in different ways, okay? In order to derive sort of some event that holds with probability greater than 0. Okay? So let's do it. So fix I between 0 and d plus 1 and h. Then I know I can write that the probability over h1 and h2, g of x plus ih I want to study x plus IH because I want to say something about it, okay? The probability that this equals the sum from j equals 1 to d plus 1, alpha j, f. Now I have x plus IH plus j j of h1 plus IH2. This is at least 1 minus 2 times d plus 1 epsilon. Okay, I'm just rewriting things. That's my x. Okay, and notice that here it is still a random step, right? Because doesn't matter whether it's 0 or not. I still have at least h1. Okay, so this is, I'm just writing like this thing, just I'm writing h as h1 plus IH2. Okay. Now you can fix j. Now it's going to be from 1 to d plus 1 and h. And I get the probability that sum from I equals 0 to d plus 1 alpha I f of x plus jh1 plus IH plus jh2 is at least 1 minus epsilon. So here I'm just going back to the acceptance probability. X plus jh1 is actually random because j is non-zero, right? And here I have some random step. Doesn't matter. So here it's is h. Is a probability of h1, h2. Oh, wait, just like here, I was just preparing myself to a union bound. And now I want to argue that with probability greater than 0, this thing happens. Okay? And because this event doesn't depend on anything that is random, then it must be true with probability 1. Okay? So by union bound, I have a probability over h1 and h2. Again, where h1 and h2 have nothing to do with x and h. X and h are fixed. h1 and h2 are the random space over which I'm working. I want to look at this expression, sum from I equals 0 to d plus 1, alpha I g x plus IH. Now, I know how each of these looks like. It looks like this. Right? So first I want to prove that this equals 0 with probability greater than 0, right? And notice that inside here I'm not using h1 or h2 at all, right? So it suffices for me to prove that whatever this thing is greater than 0. Okay? Fine. So I can I'm going to just transform the thing inside. I can sum from I equals 0 d plus 1 alpha I, and then now I suddenly open up this one, which sums from j equals 1 to d plus 1, alpha j, and then we have f of x plus IH plus j h1 plus IH2. Okay, so I just rewrote this one here for each of these guys. Okay, and now I just switch the two summations. And I also want to reorder the way that I write this. I can write it as f of x plus jh1 plus I of h plus jh2. Okay, so from here to here, nothing happened. So from here to here, I'm paying, the cost that I'm paying here is 1 minus d plus 2 times d plus 1 epsilon, right? Because I'm paying this guy d plus 2 times. I'm invoking this lemma d plus 2 times. From here to here, I am paying 0 because I'm just reordering. Okay? But then I'm going to use the fact that I have this also holds. times 0. Okay, and so from here I'm paying a d plus 1 times epsilon. Right? Okay, and if I put these two things together, I get that this is at least 1 minus, I think that expression there, 2 times d plus 2 squared, epsilon. And if epsilon is less than that, the claimed thing, then this entire thing is greater than 0. Right? Okay, good. So I find this proof really ugly. Now but there's something interesting about this proof, which is like, it really completely mirrors the analysis of linearity testing. That is good, okay? Because even though these kind of tests have sort of deeper and tighter analyses that are by far from elementary, it is nice to see that at least in a multivariate case, there is some elementary analysis that works. And not only it's elementary and it works, it actually is pretty much the same analysis as linearity testing. Okay, so that's a good thing. Okay, it's a good analysis to keep in mind. It's not going to it's at the end. I mean, it's a lot of sort of union-bound ninjas and sort of keeping track of indices. I'm actually surprised that I didn't mess up my notes somewhere. But in the end, it's really simple. Okay, it just says define a function that decodes f. It's not too far from f. G, will agree with f with high probability, and then because it does, then G is low degree. Provided the epsilon is not too large. Epsilon is not too large. Okay, it's a very straightforward way of doing it. And again, both here and here, like all we're using is this linear structure of the constraints. It doesn't matter whether in univariate or in multivariate case. So when we come back here, we actually have a test that is asking order of d queries, specifically d plus 2, for any m, right? And we have the guarantee that if epsilon is small enough, smaller than 1 over d squared, then we have this distance guarantee. Okay? If I repeat this test, order of d squared times, now I have this sort of setting of parameters that I'm interested in, right? That with constant probability, I'm constant far away. Okay? And that's d cubed queries independent of n. Okay? D for us in last week's lecture was polylog. Okay? So I cube that, that's okay, still polylog. Okay? So this is telling us that something amazing is happening here with multivariate polynomials. We have this f to the m, it's enormous. D to the m is still enormous. Okay? And we are reading like d cubed queries at random on average. Okay? And somehow the fact that on average these d cubed queries that give us local views on lines that make sense, it says that everything actually is close as a global object. Okay? So this is an example of a local to global phenomenon that is actually very deep. Okay? It's a surprising thing. If it feels like a normal thing, then you should go back and sort of think about it again. These are, surprising and sort of very fundamental statements about the structure of low-degree functions. Okay, the fact that can sort of locally test multivariate polynomials, it's sort of far from trivial. Questions about this proof? Yeah.
So this also gives you the local correction. If you avoid all these, like the d times d plus 1 times, you avoid this epsilon corrupted.
It's one way. It's a great question. So one way we're kind of implicitly using some local correction here, right? Because we're saying we have a test that reads various things, but including like f of x, right? If I move f of x on the other end, right, I could try to like pick only h at random, right, and think of that as local correction. First, I should say it doesn't work in general. So you could try to think about, I have a local test. I kind of isolate the thing. Do I have a local test, a local decoding procedure? It doesn't work in general. In this particular case, local correction actually is even simpler to think about, because if you know that you're close to low degree, you don't need to think about the steps anymore. you just pick like a random line, you read it, you decode it. And because you're close to low degree, then the decoding must kind of be the kind of the correct thing. So kind of the local, you can, in this particular case, think of local correction through these steps, but you don't have to. You can kind of decouple it and say, okay, I ran some test, doesn't matter how it runs. Now I know that I'm 10% close to low degree. And now you can sort of run your local decoding independently. And using a random line is like good enough. Local decoding is the same thing as self-correction that we discussed last time. And we don't need it anyways for the PCP that we saw, right? Okay, so here's what's going to happen next. Now we do have a PCP theorem of polynomial size. And that's great. But a lot of the motivation, so at least from the way that we've been structuring this course for looking at PCPs, is delegational computation. And the fact that you have a small number of queries that you're asking to the proof does not mean that your verifier runs in a small amount of time. Actually, the verifier that we saw last time doesn't. Like, it really doesn't run in a small amount of time. So next week, we'll see how, I think it will take us again 2 lectures, we can basically reprove, or we can strengthen the statement and say that not only can we check the satisfiability of some statement with a small number of queries, but somehow the running time of the checker is kind of on the order of number of queries. Okay? Now, saying this properly requires some care, because if I just give you the 3-set formula that you're checking, then what are you saving in running time? By the time you read the clauses and you know what you're checking, there's no saving in running time to do. You see? So we cannot talk about general clauses. We have to talk about clauses that have succinct representations. I have to give you, not clauses, but we cannot talk about general formulas. I give you a descriptor of a formula, right? I give you a small representation of a much bigger formula. From a complexity standpoint, what we're doing is we're moving from NP to NEXP. Okay? So instead of proving PCP theorems about NP, we want to prove PCP theorems about NEXP. That is the technical way through which you force the verifier to not think in the size of the formula, but to think in the size of a descriptor of the formula. Okay? So proving things about NEXP is kind of a sort of taller order. Okay? It's a harder thing to do because your query complexity has to be low and your running time has to be low. Okay? All right, that's what we're going to do next time.